to introduce our next speaker, Ryan Tully-Doyle from California Polytechnic State University, who will talk about monotonicity, convexity, and realization of noncommutative functions. Ryan, please.
All right, so thank you for those that have chosen to attend. My own attendance at these things has been spotty due to like the combination of young kids and COVID and teaching. So I appreciate taking the time to come watch me speak. And I'd like to thank Javad in particular for the invitation to speak here, and more generally the people who organized the session. I'm going to be talking about monotonicity, convexity, and realization of non-commutative functions. And this work is joint with James Pascoe. And actually, James has taken some of this work and gone further with it, which I'll point out at the end. I'd also like to thank the Fields Institute specifically, and the NSF for the funding that made this investigation possible. And then also Davidson and Kennedy for the talk that inspired this investigation, which was given at the Fields Institute on their non-commutative Choquet theory. So I'm going to be talking about problems that arise originally from the consideration of classical pick functions. So pick functions are analytic functions that map the complex upper half plane into itself. And in the classical theory, especially the theory of the 1910s, 1920s, 1930s, pick functions sat at the heart of a number of deep interconnected ideas, sort of surprising connections in some places. So interpolation problems in the Nevanlinna pick interpolation problem specifically, in the idea of the existence of analytic continuations, that pick functions have structures that admit obvious analytic continuations, in the sort of new but very powerful at the time ideas of integral representations and the use of integral representations to explore problems. Nevanlinna's approach to the hamburger moment problem, which involved analytic continuation and integral representation. And this is a move that involves the relationship between a positive matrix and the existence of a measure, which we'll see in the talk to come. And then ultimately, the relationship and the role that pick functions play in functions that are matrix monotone and matrix convex. So pick functions are sort of the glue that you can use to move back and forth between these sort of different ideas in the classical setting. And we'll see that thematic ideas in the proofs of these theorems actually turn out to bear in more general settings as well. So in the talk, I want to mention some of these classical results that connect pick functions with matrix monotonicity and matrix convexity, and then the realization or representation theorems for those functions, related generalizations of those functions in a general non-commutative setting, and then thematic ideas from the proofs in the classical setting that show back up again usefully in the non-commutative setting. So maybe the most useful, or one of the most useful and most famous results about pick functions is that they have a very nice integral representation. So through the talk, pi is going to represent upper half planes of various types. This is just a classical complex upper half plane pi. A pick function is an analytic map that takes the upper half plane into itself. In the core theorem in the classical setting, one of the core theorems is called Nevanlinna's representation. This is the Nevanlinna representation, for example, in Lax's functional analysis. And what it says is that f is a pick function if and only if, so this characterizes the pick functions. You have a scalar, a positive number, and a positive finite Borel measure mu, subject to the condition that the integral of 1 over t squared plus 1 is finite, this normalizing condition. So that for all z on the upper half plane, you have this realization theorem, this integral representation, and that a, b, and mu are uniquely determined by f. So in some sense, the function is carried by this measure mu. One of the reasons why this representation theorem is so useful is that it's actually pretty easy to see just algebraically that the kernel of this integral is algebraically a pick function. If you plug something in that has positive imaginary part, just by computation, you can show that it preserves the the imaginary part being positive. And this is often invoked in continuation arguments, where a typical line is to show that something has an integral representation on, say, the reals, and then structurally it's just immediately obvious that it analytically continues to whatever space you're letting stand in for your upper half plane. So the first connection that you see with positive matrices here, this is pointed out by Donahue in his classic book on matrix monotone functions and analytic continuations. You get this connection between the integral representations, Pick functions, and positive matrices by way of Pick's observation that for a given analytic function on the complex upper half plane, that for any collection of points in the upper half plane, that this Pick matrix is positive semi-definite. So this observation, of course, leads immediately to the question of Nevanlinna Pick interpolation theorem, but also it provides the first evidence that there's a relationship between positive matrices and the behavior of Pick functions. And in fact, Löwner's theorem I think the original proof of Löwner's theorem goes by using a limiting argument of Pick's observation about endpoints. So a matrix inequality just leverages the fact that there's a natural ordering on the self-adjoints. So if A and B are self-adjoint, then we say that A is less than or equal to B if B minus A is a positive semi-definite matrix, and A is less than B if B minus A is positive definite. If I say something is positive through the course of the talk, typically I mean positive semi-definite unless otherwise noted. So we're going to be interested in evaluating functions on matrices to see the relationship between matrix monotonicity, matrix convexity, and analyticity. And so I have to set up a functional calculus. So if f is a function defined on an interval, then given a self-adjoint matrix A with spectrum in that interval, and we can diagonalize it by a unitary, then we can define an expression for f of A with the formula where we take f and apply it to the diagonal elements. And the one motivation for this is actually just equivalent to plugging the matrix in if f happens to be a polynomial or a rational function. So this extends that idea. And ultimately, we want this to apply in analytic settings. And so there's like power series running around in the background. So under this definition, we should note that f has a couple of useful properties, namely that f preserves direct sums and f preserves unitary conjugations. So one of the core questions of the 1920s and 1930s was to relate functions evaluated on matrices to their complex analytic behavior. And so the two classical families we're going to consider here are the matrix monotone functions and the matrix convex functions. So f is matrix monotone if I fix some level n, so I pick an n by n matrix, or I pick a level, I pick a pair of n by n self-adjoint matrices A and B that have spectrum in AB, so they can be evaluated via the functional calculus, then A less than or equal to B implies that f of A is less than or equal to f of B. So this is in analogy with monotonicity in one variable, or in a scalar variable. And we say f is matrix convex whenever f evaluated on n by n matrices via the matrix functional calculus is a matrix valued convex function. So that is f, we're using midpoint convexity here, which is equivalent to convexity, the settings that we're working on. So f of the midpoint of A and B is less than or equal to f of A plus f of B over 2 for all A and B with spectrum in AB. It's important to note here that we are actually genuinely working with a new class. The matrix monotone functions are a strict subset, and the matrix convex functions are a strict subset of the monotone and convex functions, respectively. This is easy to show with computation. So, for example, you can write down the matrices 1, 1, 1, 1 and 2, 1, 1, 1. So say A and B, and then the function f of x is equal to x cubed is everywhere monotone increasing. But if you evaluate f of A and f of B, and then you subtract those, you end up with a matrix that has negative determinant. So one of the eigenvalues is negative, and that violates the ordering. So even though f is is monotone everywhere, it's not matrix monotone. Okay, so matrix monotone functions are a strict subclass. So Löwner's theorem, originally proved with matrix analysis, gives a characterization of matrix monotone functions. So a function f on an interval a to b turns out to preserve these monotone matrix inequalities. It's matrix monotone if and only if f analytically continues to a pick function by extending off the interval where it's originally defined to the entire complex upper half plane. And I should point out here that I want to emphasize that this is a matrix monotonicity is a condition that holds on all levels, right? So it's any level that you choose, you have to preserve the matrix monotonicity. And so, of course, Löwner's theorem also is a theorem about not just analytic continuation, but it's a representation theorem as well because of Nevanlinna's representation. So matrix monotone functions also are functions that have Nevanlinna representations. So one straightforward proof of Löwner's theorem runs through Nevanlinna's solution of the hamburger moment problem. And what the hamburger moment problem asks is, given a set of moments, when can you construct a positive measure on the real line that possesses that sequence of moments? And the answer turns out to be in terms of the positivity of a related Hankel matrix that you build from the moments. And the proof of Löwner's theorem invokes the hamburger theory, Nevanlinna's solution to the hamburger moment problem, specifically to use the resulting measures to construct the representation. So this is sort of a thematic idea that's going to show up again in proofs of the more complicated theorems, that you start with something geometric about matrices, and then the matrix convexity or matrix monotonicity. You can characterize that in terms of positivity of some Hankel type construction, and then that thing is used to construct an analog of a representation in a measure that you can sum up into a global object. I'll say here that the integral representations of not the Nevanlinna type, but not the Nevanlinna representation itself, play a key role in this particular proof. This is chapter 9 in Donohue's matrix monotone functions book, and it's actually the inspiration for the approach that James and I took when we looked at the non-commutative Löwner theorem for the first time. So Löwner student Kraus built a technical advancement over Löwner's theorem, an extension to a more restricted, more structured class of functions. So in the same way that monotonicity is controlled in some sense by the first derivative of function, convexity is controlled by the second derivative, you can think of this theorem, or I think of this theorem, as sort of the derivative of Löwner's theorem, the derivative of the Nevanlinna representation. So what Kraus showed is that if you have f defined on an interval, then f is matrix convex if and only if f has this particular integral representation. And so this is not the same as the Nevanlinna representation. It's derived from the Nevanlinna representation. But again, you have constants a and b, mu, a finite measure supported on the closed interval. And again, it comes with a continuation theorem that says that once you have this representation, you can compute that this function analytically continues to the upper half plane. Basically, the way that Kraus did it was he leveraged the machinery of Löwner's theorem. So he showed that matrix convex functions had to be C2, and that let him work with f over x, show that function as matrix monotone, and essentially, because he had two derivatives to work with, he could derive or differentiate the Löwner representation to get this one. But the thematic idea here is that the argument that Kraus used followed from the Löwner theorem. So the same machinery that you use to build the Löwner theorem, you can also build the Kraus theorem with. And again, that's a theme that's going to show up in that there may be some sort of unified approach that's going to show up when we talk about the Royal Road. Thematic ideas from the classical proofs that I want to highlight, and there's particular proofs, are those that we can actually bring forward into the non-commutative setting. So there's lots of proofs of Löwner's theorem in one variable. Barry Simon has a recent monograph, which I think has 10 chapters. Each chapter is a different proof of Löwner's theorem from a different angle. There's a very nice paper of Hansen called The Fast Track to Löwner's theorem. So which proofs are the ones that have elements that we might think we can carry forward? Well, Monotonicity and convexity give rise in certain classical proofs give rise to these families of positive matrices, and there's quite a number of structural theorems about very powerful structural theorems about positive matrices that we can leverage in several variables that we might because of the existence of those structural theorems, we might decide that these are this type of argument might lift into a broader setting, particularly because once we have the positive matrices, those in the classical theorems typically give rise to a measure and a representation against that measure that is real analytic. And then that real analytic structure it can be shown just algebraically often or through manipulation that it analytically continues. And so one of the inspirations for this type of approach, or following this type of approach in a broader setting, of course, is Agler's original approach in the late 80s and early 90s, where he showed that you could work with Hilbert spaces in lieu of working with measures and carry the structure of these integral representations forward and then work with them, but you have to be willing to work in an operator setting instead of a measure setting. But that these results very naturally extended to several complex variables. And ultimately, the other part of this that is sort of fascinating is that these results are automatic analyticity theorems in some sense, that the geometry of the function or matrix geometry of the function forces the representations of these functions to have structures that analytically continue. So the question is, can we do this in the same type of way in a non-commutative setting? So can we leverage complex analysis, the ideas of these classical complex, these theorems of complex analysis in the non-commutative setting? So then, does this heuristic generalize? Can we do something where geometry leads to some kind of positivity condition that's going to lead to something like a structure against a Hilbert space? And some evidence that there might be some kind of unified approach or complex analytic approach is just given by the wealth of representation theorems that we actually have. So there are a lot of representation theorems in non-commuting and commuting variables for structured functions. The imposition of some sort of geometric condition tends to force realizations to hold and for those realizations to be analytic. So here's a subset. This is by no means exhaustive. These are just papers that I've read recently. So the first work that I did on this was with Agler and Young on Nevanlinna representations in commuting variables. And then James and I and Miklos Palfia sort of took the commuting ideas and lifted them to the non-commutative setting, essentially by aping the James and I anyway followed the proof that was laid out in the Donahue text, where you pivot through a moment problem to get there. There's Kraus type representations as well. So Houghton, McCullough, and Vinnikov in 2006 proved a realization they call butterfly realization for matrix convex functions that are rational. And then later work by James and I, Palfia and Gall, and Palfia solo in 21. Quite a bit of work on partially convex functions and their representations, represented by a group that includes Jury, Klepp, Mancuso, McCullough, and Pascoe. A lot of other work on convexity with Houghton and Vinnikov and Joe Ball and Dmitry Kaluzhny-Verbovetsky. Pluriself harmonic functions in the work of Dim, Houghton, Klepp, McCullough, and Volchich, and later commented on by Pascoe, and more, right? That we have a lot of representation theorems available, and almost all of them involve a move where you have a function that's defined locally and has some sort of nice behavior. The realization holds locally, and then it rolls out to some larger domain, which again is reflective of this idea of automatic analyticity. Furthermore, these functions turn out to be, and again, the inspiration for investigating the subject originally is that between the work of Houghton, McCullough, and Klepp and collaborators on the one hand, and Davidson and Kennedy on the other, in their invocation of, or their use of the matrix convex functions in their Choquet theory, these are functions that are being actively used. And so both of these provide impetus for looking more closely at what we can say about them. So if I want to talk about functions in the non-commutative setting, I should probably define it. So let's let this first definition is going to be at a high level of generality. So let V be a real vector space. We're going to define the matrix universe over V to be the sort of graded set gotten by taking the n by n matrices over the complex numbers and tensoring with V. And we define the real matrix universe over V to be the symmetric subset of those. And this induces an ordering, just like the Löwner ordering on the self-adjoints, where we say A is less than or equal to B if B minus A is positive semi-definite as an element of SNC tensor V. And if that's overly technical for understanding what's going on in the rest of the talk, then one way that you can hold in your head is that this is really just a generalization of the standard matrix universe, where the set MD is just D tuples of n by n matrices, and then the real matrix universe sitting inside that is D tuples of symmetric matrices. Use the more general setting so that you can deal with things like block matrices. But if you need an analogy to carry in your head as we go forward in the talk, just think about the matrix universe as being D tuples of matrices, and the symmetric part of that, or the real part, the real line that sits inside of it, as being the D tuples of the symmetrics. And in that setting, the Löwner ordering is going to hold entry-wise. Oops. Okay, so non-commutative sets are sets that are built to interact well with free functions. So a free set here is going to be a set D contained in the matrix universe MD that has the property that if we start with two matrices in D, we can direct sum them and stay inside. So sort of this gives us closure under level-wise operations between levels. And that X being in D implies that a unitary conjugation of X stays inside D. So we shouldn't be, we can't change basis and leave the D is the idea. And properties that we associate with domains, we just define level-wise. So we say that a domain D or a set D is open or convex whenever D intersected with each particular level is open or convex. Likewise, we're going to define functions. So D is going to be a free set, and we'll define, we're going to use the word real. I'll explain what the word real here is doing in a second. So we're going to define a non-commutative function, f from D to M, to satisfy the properties that if we're talking about matrices, the f is graded. So it takes matrices, tuples in n by n matrices to a matrix of n by n, that f respects direct sums, and that f respects unitary conjugation. And here, this basically exactly comports with those functions that satisfy the matrix functional calculus. I should point out here that the usual definition of free functions that you see in most talks involves f respecting arbitrary similarities instead of arbitrary unitaries. If you make the further assumption that f is complex analytic, then you recover that definition, and so this is in agreement. So we also get an analog of the complex upper half plane in terms of these matrix-like objects, just using the natural ordering. So we define the upper half plane, again, thinking about it as tuples of matrices, just to be those matrices where if I use the typical definition of the imaginary part of a complex number, but I put these tuples in entry-wise, that the resulting object is positive. And then with that definition of the analog of an upper half plane, we can say that a free pick function is a free function f that takes this analog of the upper half plane in D variables, in D tuples into the one variable matrix analog of the upper half plane. So we also are going to need a notion of how to bring the matrix geometry forward, but this is the virtue of this setting, is that these are very natural to write down. So we say a free function f is matrix monotone in this sort of free setting if a is less than or equal to b, implies that f of a is less than or equal to f of b. And a free function f is matrix convex if it carries the same definition it has in the scalar case. That is, the midpoint convexity on matrices condition still holds. F of a plus b over 2 is less than or equal to f of a plus f of b over 2. So a theorem due originally to James and I and to Miklos Palfia gives a Löwner theorem in the free setting. That is, we get a characterization of those functions that are matrix monotone. So if D is a convex domain in SD, so this is the analog of a real interval here. So we're working in the symmetrics, which are sort of our analog of the real numbers. A free function F is matrix monotone if and only if F analytically continues to the upper half plane as a function in the free pit class. And this is essentially so I should point out here that, like, in the original proof, we had to assume a certain regularity condition on F. We assumed, I think, that F was C1, and Miklos Palfia didn't have to make that assumption. James in 2018 came back and proved the same theorem, dropped the regularity assumption, and did it in probably the most general possible setting in the context of real operator systems, which are supported by our definition of free sets and free functions. So in both contexts, we get that matrix monotonicity is characterized by analytic continuation to a complex upper half plane. And I want to point out that in this argument, in our first go at a proof of Löwner's theorem, we ran through much the same lines as the classical approaches, that we used matrix monotonicity of F to establish a Hankel type condition on a matrix of coefficients. And then with that matrix of coefficients, you can construct a Hilbert space that stands in for the measures in the classical theorem. And you get these models called hamburger models that essentially end up summing up to a function that obviously analytically continues to the upper half plane. So it is, again, a result of automatic analyticity type setup. And just as in the classical theorem, this also comes along with a non-commutative version of the Nevanlinna representation. And you can see here, this is the special case of it that agrees with the Cauchy transform. But the idea is that you end up with this kernel that looks like 1 over t minus z inverse. And the measure, the role of the measure is being played by this ambient Hilbert space and the operator, oops, what did I do? And the operators that are sitting inside of it. Now, one weakness in the approach that we took, not weakness, but this is a very Hilbert space theoretic argument to prove both the Nevanlinna representation and the Löwner's theorem. There's a lot of Hilbert space machinery to do this. And likewise, in the Pasco's 2018 result, he actually uses the commutative theorem to prove the non-commutative theorem, which in some sense can be seen as sort of an unnatural part of the proof. And again, both of those justify maybe looking at something more natural. I'll also point out that the butterfly realization falls into the same category. So Helton, McCullough, and Vinnikov developed this, I'll call it Kraus flavor, but it really is a Kraus representation for rational matrix convex functions in 2006. So now we start with a non-commutative rational function, which is not, but can be thought of as a quotient of non-commutative polynomials. We start with this function defined on some domain containing 0. If R is matrix convex near 0, then R has a realization of the form, and I'll put it down here so you can see, of the Kraus representation, classical Kraus representation. So we get a realization theorem in terms of these matrix objects that essentially recapture the spirit of the classical Kraus theorem. In particular, the kernel of this integral, the x squared over 1 plus tx, is at least in spirit identical to this conjugation by a square and then this resolvent type object that sits inside of it. I will point out that Helton, McCullough, and Vinnikov's proof of this is incredibly elegant and also a very long argument to show that all these things make sense. So guided by the idea that, so where does the name Royal Road come from, right? So I'm going to talk about the Royal Road approach to these theorems, which is an attempt to use complex analysis and more of the classical theory, the one variable theory, to work in n variables. So the apocryphal story about Ptolemy is that he was complaining about how hard it was to learn geometry. So Euclid told him, "There's no royal road to geometry." And it turns out there is a royal road to Löwner's theorem in several variables and related geometric theorems in several variables, which is the one variable theorems. And so what I'm going to describe next is an approach, the royal road, of applying classical one variable theorems in a way that coheres into results in the n variable setting. So that's the goal of all of it, is to be able to apply these one variable theorems. So what the royal road does is it attempts to axiomatize the central properties of these matrix convex, matrix monotone functions, these geometric conditions, right? What are the properties of these functions that makes the automatic analyticity of said functions attain? And so, you go looking at these theorems, and what you see beyond the existence of these positive matrices is that we're always starting with functions that have some kind of structured domains, right? Usually convex domains. We're starting with an interval. And then we have some kind of good local behavior. So good local behavior, local boundedness or local domination by derivatives. So in some sense, the derivative of the function is controlling the behavior of the function. And then finally, a move that's made in a lot of the classical approaches to these theorems is that they're amenable to approximation in some sense, that you can convolve them with smooth functions and stay inside the function class. That's something that you just do when you're doing one of those arguments, but you don't necessarily note that it's a feature that shows up over and over again. And because we're trying to work by starting in some big general setting and cut down to small pieces, we're going to need a tool that allows us to localize, show that functions are analytic or have the right kind of structure, and then glue those pieces back together in a way that they cohere into a sensible whole on the entire domain. And at the heart of that is Pascal's surprising and powerful theorem for analytic continuation in non-commutative settings called the wedge of the edge. So there are several versions of this paper in slightly different settings. You should see the one in the Bulletin of the London Math Society or the Canadian Mathematical Bulletin. And the wedge of the edge results basically give us a way to start with, we just need some little sliver where we have analytic behavior, and then we can use that behavior to roll analyticity out to the whole domain. So that's the trick. The axioms are going to let us work locally. The wedge of the edge theorem is going to let us take our local investigations and build them back up into global. So I'll give you an idea of what these axioms actually look like. Here you can think a dominion is just some set of domains. In some sense, these are recapturing the behavior of intervals, like open bounded intervals in the real line. Translation invariance, you stay in a convex set, for example. Scale invariant, closing under intersection doesn't let you leave the type of domain that you're starting with. You can localize. And so the idea is, again, that we're sort of capturing the behavior that the intervals A, B are playing in the classical theorems. And this is useful because it turns out to be the case that the class of convex sets, for example, in RD, is an example of dominion, as is the class of all open sets. And likewise for various matrix domains as well. The sovereign class is a set of functions that sit over a set of domains contained in some kind of dominion that satisfy these axioms that, again, are selected to support working locally, and then the application of the wedge of the edge theorem to bring things back up again. So I've written, those of you that have seen the 20-minute versions of this talk have probably seen these definitions before, and hopefully nobody's ever tried to read these definitions. I'm going to try to give you an idea of the names of the properties and what job they're doing when we're constructing this sort of attempt to apply things at level 1. If you're interested in the actual definitions, you can go read them in the paper. They're here for completeness. So the basic idea is that I need to be working with functions that I can approximate and work with locally. So closure under localization is going to give us the way to drop down and stay. So if you start convex and you restrict, you're still convex, for example. Closure under convolution is a way of making sure that we can approximate with functions that carry whatever smoothness we need. Local boundedness and one variable knowledge, basically what those involve is injecting a parameter into a function in the NC case to turn it into a one variable function. So I need to be able to inject some parameter and work on a line, say, and then the fact that once I can do that, the automatic analyticity is built into the fact that that one variable injection turns out to analytically continue. And that's one of the things that we're going to need in order to apply the sort of classical theorems. And then finally, we need some sort of method of control. So some kind of function that controls the size of f in norm, and that function has to be built so that the wedge of the edge theorem can be applied. So the idea is that once you set up the set of axioms, if you've chosen them correctly, functions that meet that set belong to a sovereign class. And the justification for the axioms comes from the fact that those functions that meet the axioms are precisely those functions that are automatically analytic. So the main result of the Royal Road method asserts that functions in a sovereign class are real analytic functions. And that means that if you start in a sovereign class, you starting for free, say, with a power series. So the basic idea of how the proof of this works is essentially what I've already said, right? That the idea is that functions in a sovereign class can be worked with locally, where they're analytic on these little one variable slices or one-dimensional slices. One variable parameterization, the injection of this parameter, gives you local analytic continuation, which opens the door for applying things like the one variable Löwner theorem or the one variable Kraus theorem. And then that gives you structure that you could potentially lift to the broader setting. And the reason that you can do that is because you have local control, which lets you use the wedge of the edge theorem to sort of glue all the pieces back together again. So you use the wedge of the edge theorem to work per level, and then again to restructure the entire thing on the whole free domain that you're working on. If you're interested in looking at how this argument works, it's actually easier to follow in the paper that we wrote called the Regal Path, which is a simplified version of these axioms that's used to derive the commuting Löwner theorem from the non-commutative theorem, which in some sense is a patch of it's the correct way that things should be done. I think it's that and a sort of exciting development in the function theory of non-commutative function theory recently is that non-commutative theory is being used to investigate commuting questions. So, for example, in the Regal Path paper, and quite a bit more evidently and with quite a bit of excitement in the series of papers by Martin and Jury, where they have been getting some results in commuting function theory by using the work they're doing in the non-commutative case. So just to give you an idea of kind of precisely what's going on in the background, we're going to try to involve the derivatives of functions here to develop a norm that's going to control the functions locally. And it's a little bit illustrative to see how the matrix convexity and the matrix monotonicity give you what you need in order to apply the wedge at the edge theorem and do this sort of reconstruction of one-dimensional data. So you can define this object called the positive orthant norm. And the positive orthant norm turns out to be exactly recover control functions that you need for matrix monotone functions. So in some sense, the most difficult thing about showing that a function satisfies the axioms is showing that it has a control function. So the matrix monotone functions, sort of pleasingly, are controlled by the norm in terms of their derivative. And the matrix convex functions, likewise, are controlled by a control function that involves the norms of the first and second derivatives, which is in keeping with what we know about the relationship between monotone functions and their derivatives and matrix convex functions and their second derivatives. So once you establish control functions and you can show that matrix monotone functions and matrix convex functions both satisfy those axioms, they're both in a sovereign class. And what that means is that starting with matrix monotone functions starts you with a power series. And if you have a power series, you can do complex analysis is the idea. Representations now are going to follow along similar lines to the classical theory. That once we know that we're starting with something that has a power series, we can use positivity of some kind of related Hankel type. We can use that to show that we've got positivity of some kind of related Hankel type construction, and then use that, usually via some sort of GNS construction, to construct a representation where Hilbert spaces are standing in spaces for measures, and then the structure of the representation forces the analytic continuations to exist. very much in keeping with the classical approach to these questions. So I'm going to specifically focus on the approach to this for convex functions, how that works. Although the Löwner theorem follows similarly, or is very similar in construction. So in one variable, of course, convex functions are characterized by positivity of the Hessian matrix. And the same characterization turns out to hold in the NC setting for the appropriate notion of Hessian. So for a matrix convex function f, you can see that the second derivative of f in the matrix direction h is positive, right? So we start with a matrix convex function that the second derivative is positive. And that means that if I could start with a power series and take its second derivative, I have something I can say about the coefficients of that, as long as I can write it in some sort of symmetric way. If you're interested in looking at the role second derivatives play in convexity, a good place to start with that would be the Helton, Klepp, and McCullough survey on real analytic geometry from 2013, and a whole raft of related work on matrix convex functions prior to and following from that. But that's a good place to start if you haven't seen that before. So the approach to the Kraus theorem essentially works in the following way. It's very closely related to, I mean, we're following a path that's been trod before. So this is related to Nevanlinna's approach to the hamburger moment problem. We start with a power series that we're guaranteed to have because matrix convex functions are in a sovereign class and therefore automatically real analytic. Then we can just write down what the second derivative of f looks like in the direction h. So this is a standard computation on the power series. And I know that that power series has to be positive because f is matrix convex. So the analyticity gets us the power series, the convexity gets us the positivity. And using this algebraic trick, we can actually get that x to the gamma out of the picture. This trick, I didn't believe it the first time I saw it, but you just evaluate this expression on the matrix x0, 0x and on the direction 0h, h0 and restrict your attention to slot 1. That actually lets you drop the gamma. And what you get is a Hankel type matrix. And some relation on the coefficients of the result. And that Hankel type matrix turns out to be positive. And so at that point, once you've established the positivity of this matrix, you just follow the usual line of argument. You construct a related Hilbert space, and then you go through a GNS construction. And the result is just by algebraic computation, you get a Kraus theorem. And since we started with sort of a generic with a general matrix convex function, we recapture the Helton, Klepp, and McCullough result for rational functions, but now for a general function or a general free function f. So the theorem says if f is locally bounded matrix convex function defined on some matrix convex set of self-adjoints containing 0, then you can find self-adjoint operators ti, vector qi, scalar a naught, and a linear function L, so that again, we basically recapture precisely the Helton, Klepp, and McCullough result for rational functions. And it has two virtues, right? The first is that one, it is for a general f instead of a rational f. But second, the argument is actually much more complex analytic, and doesn't require going through the very technical argument that was used to establish this in the 2006 result. And this is also reflected in the new proof of Löwner's theorem. Also has the same kind of move embedded in it, where the original constructions are these delicate Hilbert space constructions. But by working with the one variable theorem and then building back up to the n variable case, you can use complex analysis instead of having to do so much operator theory when you're doing these constructions. So I guess before I get to further considerations, I want to re-emphasize here sort of what the big theme of the Royal Road approach is. And as the field of non-commutative function theory has matured, how we start seeing these kinds of new approaches to proofs of these theorems evolve. So in our first efforts to prove the non-commutative Löwner theorem, and in the work of Helton, Klepp, and McCullough in the rational case for the Kraus theorem, the idea basically is to construct an n variable setting and then use n variable geometry to reproduce the behavior of the one variable theorem. So you're starting by building the space and then looking for the behavior in that space. And what the Royal Road theorem does is let you avoid a lot of that construction by reversing the process, by using something about the intrinsic nature of free functions and free sets to drop down into one-dimensional pieces, and then apply one variable theorems and do complex analysis. So thematically, it's a very powerful, at least pleasing, I don't know, powerful, but very pleasing way of working. And it gives you access to tools that you don't have if you work in the way that, for example, we started when we were graduate students. So coming out of this work, there are some questions that I'd like to leave the audience with, questions that I've been thinking about, questions I've seen James pose in other talks. And then I want to point to like a new theorem that suggests why any of this might work in the first place, something intrinsic about the nature of the free sets and free topology. So the first question is, and this is a question that James has posed in other talks. So the Löwner-Nevanlinna representation for an analytic function turns out to pivot to the construction of the realization, the construction of the analog of the integral representation. Turns out to pivot, just like in the classical case, on the positivity of this Hankel type matrix built out of the coefficients of the power series. And likewise, for Kraus functions, we consider the positivity of this Hankel-like matrix that arises from the second derivative of the power series instead of the first. So one question to ask is, well, if the Hankel matrices are somehow encoding the geometry, are there others? Are there other sort of these structured matrices we can find, these Hankel type matrices we can find that give rise to other geometric conditions that haven't been considered yet? Second is, and this is sort of a lighter question, but one that I think is amusing to ask, is the matrix monotone functions are a sovereign class, in part because they're controlled by this norm in terms of their first derivative. Matrix convex functions have this real analyticity property or automatic analyticity property because they're controlled by norms involving their second derivatives. So my sort of light question is, given that the internet has decided to call the third derivative of function jerk, is there a family of corresponding jerk functions and that are a sovereign class? Do they have a realization, and what are they? And then finally, and this is maybe the big deal and a pitch for people to see James's talk tomorrow, is that the Royal Road approach, this idea of the analytic continuation and the ability to use the wedge of the edge theorem to go back and forth between one-dimensional information and global information, and the general theme of local to global expansions happening in these realization theorems, that's a lot less surprising, I think, when you see this universal monodromy theorem. And so which of course underlies, I think, morally, at least the existence of these analytic continuations. So recently Pascoe showed that a connected open free set satisfies the monodromy theorem. And the consequences of the free universal monodromy theorem are quite striking. They tie a lot of local theorems together with realization theory. They have implications for cohomology and topology, and so it's a sort of a new way of sort of looking at what's going on and what the connections are that are sort of built into the setting of free analysis. And so if you're interested, I think James is talking about that tomorrow, or at least in part, and it would be interesting to see sort of where the work that we did here goes in the work that he took from here. So yeah, thank you for your time. I appreciate you coming, and I hope I've shed some light on what's going on in these papers.
Thank you, Ryan. It was a wonderful talk. Questions, comments, suggestions? If there are no questions, let's thank Ryan again.